I depart going in the tangential direction. Okay, so of course that angle there is 90 degrees before the force tangential and force radial, and the force we're actually applying is somewhere in between there, right? If I had applied this force all the way in the FR direction, I would get nothing, and if I had applied it in this tangential direction, I would get maximum rotation, but I'm somewhere in between, right? And we're going to call that angle between force radial and the actual force theta. Okay. So now, just to draw this a little more clearly without the extra bits, so I have force tangential. Again, I'm moving the vectors around. I have my initial force vector there, or rather my non-decomposed force vector, and I have my force radial there. I just realized that I don't need to be talking in my lecture hall voice because I'm not in a lecture hall, so hopefully if I've been blasting you with my voice up until now this is a little better. Okay, so I have my force tangential, of course, just equal to sine theta f, right? Where I lost the vector arrows on top because I'm just talking about magnitudes here, right? This force radial, it's unimportant because it does nothing to the system, so it just gets thrown away. And then I could just then say torque equals force tangential times r, right? And then this is force sine theta r and f script L. So script L is defined to be sine theta r, and this is what's called the moment or lever arm. Okay, it's kind of an awkward notation, and I don't use it, but you may see it again and think, well, Professor Plick never taught us about this. I'm just going to mention that this is what this is called, right? Just in case you see it somewhere. But it's not really necessary, at least right now, to use it at all. Okay. Right. So we can get at this torque by just taking, right, sine theta r times the total force, decomposing it as we normally would. All right. So a special case of torque can be due to a gravitational force. So we've been looking at this object straight down, right? Gravity's not doing anything to this because gravity has no component in the tangential direction. It's all in this third component, which we haven't even talked about, going in. And of course, pushing in on the pivot from the top or from the bottom isn't going to do anything, just like pushing in towards the pivot this way isn't going to do anything, right? But what if this thing was rotated, right? What if it was in some gravitational field and the gravitational field could do some work on it and cause it to rotate? Well, I imagine I have some weirdly shaped object, whatever that might be, right? And then I attach a pivot here, okay? And the force of gravity is pointing down, so now we're looking at something from the side. So this thing, of course, is going to rotate under the force of gravity like so, right? If I take, it's going to be difficult since I'm doing this from above, but if I take my hobby book and I relax my grip a little bit, of course, it pivots around my thumb under the force of gravity. Okay? So when we have something like that, something that's just held by one end under a gravitational field or something similar, we say torque gravity is mass gravity times the x distance of the center of gravity. So the center of gravity most often is just the center of mass, right? So suppose we have our center of gravity here, right? And this guy, of course, is going to rotate along with the rest, and if we want to calculate the torque due to gravity, we only take this x distance, right? We don't take this distance from the pivot to this point, we just take the x distance, right? That distance that's perpendicular to the direction that the force of gravity points in, right? So this is the same thing as only taking the tangential component over here, right? One thing that I want to mention, just while we're talking about various things that have to do with rotation, is what's called the no-slip condition, which is something we've been using some kind of implicitly up until now, which is just saying that if I have some object rolling, it doesn't slip, right? The rotation is totally matched to its linear velocity by the radius of the object. This also applies to ropes and pulleys and things like that. You might imagine that I have some sort of pulley, right, with a rope or chain or something wrapped around it, right? If I I'm pulling on this rope and it's moving, and the pulley wheel is also rotating, well then the velocity tangential equals r omega, as you're used to, and of course then acceleration tangential is r alpha, right? So this is just saying that this rope doesn't slip on this pulley, or that ball that's rolling down the inclined plane doesn't slip, right? And I have this matching between the tangential and velocity and acceleration, and the angular velocity and acceleration times this radius here. So in this drawing, this would be r, right? Okay. Just something important to mention real quick. All right, I got 20 minutes left. I guess timing doesn't matter too much since you know this is happening asynchronously. I doubt many of you are watching this at 8 a.m. in the morning, if I even get it uploaded by then. If I figure out how the computer machines work. Okay. You know, just by myself, there's no one to laugh at my stupid jokes. My cat's asleep. He doesn't really laugh anyway. Okay. So we can use torque to define a rotational form of power, right? Remember when we were talking about linear kinetic energy, one of the things that was important was the idea of power, because a lot is lost if we don't talk about how quickly something happens, right? We need to look into that too. So the infinitesimal unit of work, this dW, right, is going to be F ds. This is the infinitesimal path, and this is the force as normal. And then I have F t, right, because I'm only worried about the tangential because we're talking about torque and rotation, ds. And then we can change this ds into something in terms of theta, because of course we're interested in angular quantities. So we have ftr d theta, right? This r comes about because remember when we were talking about the introduction to the circular polar coordinate systems, whenever we have a d theta and an integral, it comes attached to this r here, right? This r is called a Jacobian, right? And takes into account the fact that paths are different for different distances from the pivot, okay? And then, of course, this is just our torque. So we get infinitesimal unit of work equal to torque infinitesimal rotation. Okay, so that's helpful when we're writing integrals that have to do with rotational kinetic energy. And now, of course, we're talking about power. So we know that power is defined as dW dt, right? The rate of change of work with respect to time, and thus the rate of change of energy with respect to time. And we just plug in stuff from up here, right? And we get torque d theta dt, which then is just t omega. Rate of change of the angular position with respect to time is angular velocity. So power is equal to torque times rotational velocity. Okay, so that's helpful when you're driving around your pickup trucks in the mud or whatever it is that people do with muscle cars or trucks or whatever. Okay. So let's go over some examples. Drink a tea. Okay. So let's assume that we've got that uniform rod again, right? And now it's attached to some pivot. So I have some sort of contraption, right? A ball and socket joint or something like that. And for whatever reason, I've attached to that some long, uniform, thin rod or something. Okay. So if force of gravity is pointing down, of course this thing's going to rotate, right? It's going to fall and rotate. So we're going to define our y direction as this way. So positive y is going down instead of up. We have our center of mass here, which is, for this uniform object, the same as the center of gravity. Force equals mass times gravity, so we'll get some force there. And this has some distance, L. Okay. All right, so I'm just going to read the problem from the book now, and then we'll get started on it. A uniform thin rod of length L and mass M is pivoted at one end. Boop. It is held horizontal and released. Effects due to friction and air resistance are negligible. A. Find the angular acceleration of the rod immediately following its release. And B, what is the magnitude of the force exerted by the rod by the pivot at this instant? Okay, so this is a little trickier, thinking about what that means. And what that means is that as this thing is falling, as it's pivoting, the reason that this half stays in place is because this pivot is applying a force in this direction, right, counter to the direction of the force of gravity to keep this point stationary, right? So what is the force on this pivot as this thing falls? So I mean, if most or many of you want to be engineers, these kinds of questions are critical, right? How much force am I putting on this pivot here? Is it going to stand up to that strain? Is it going to break? Is it going to wear, et cetera, et cetera, et cetera? Okay. And so the reason that the problem asks for the angular acceleration of the rod, I'll write this down even, immediately following release. Right, is because as this thing falls, right, all the geometry of this will change. This will change. The angular acceleration will change. So it's just a more complicated problem if we don't just say, okay, just the one instant, just as it's starting to fall. What are these quantities? Okay, so we're doing a new type of problem now, right? We're accustomed to problems like this without the rotation from our linear kinematics and linear force equations. And the first thing we always do when we're talking about that, using Newton's laws to solve problems, is we write down net force equals mass times acceleration of the center of mass, right? So now the version of that we have is, right, the sum over all external torques, right, is equal to I alpha. So that's our Newton's second law for rotational systems. So we just have really one torque coming into play here, which is going to be the torque due to gravity. And that's just going to be mgl over 2, right? Remember over here, right, we're just taking this x distance, center of gravity, and times mg, and that's what we have here, right? Of course, that x distance is just half the distance of the rod. The reason that this becomes tricky if we're talking about the continued motion of the object is because as this thing falls, of course, this x distance decreases. So all of these equations would change with time, so we would have to do an integral derivative or something like that. So we're not going to do that in our first example. Okay, so we're just going to take the simpler case. So we're going to look up the moment of inertia of this rod held by its endpoint, which we had also in the earlier problems, 1/3 ml squared. Okay. And then I just directly apply this equation here. Right? So we want to know this angular acceleration. We've got all the other information now. Alpha equals torque due to gravity. So I'm just inverting this equation here, divided by the moment of inertia. And now it's just a little plug and chug. mg L divided by 2 divided by 1/3 ml squared. And we get 3g divided by 2L. And that gives us the angular acceleration at the moment that this thing begins to fall in that y direction. Right? Okay. So the next bit of the problem, can I squeeze this in the same piece of paper? No. All right. Next part of the problem is we want to know what's that FA. Okay, so we're going to write the sum over all external forces, right, in the y direction. So force sub external sub y, both of those things, and this of course is going to be m a c m in the y direction. Okay, so we defined our y direction, the positive direction, as being down, right? Because that's the motion, that's the direction the motion is going to happen in, so it's just more convenient to write it that way. Okay. And then we can just rewrite this as mg minus fa equals macm y. Okay? So all the external forces are just the mass times gravity, force of gravity on the center of mass, and in the opposite direction, the force exerted by this pivot. All right, so we have mg minus f sub a, right? This f sub a, that points in what we have defined to be the negative y direction, which in this case is up. Okay. So now we have a center of mass equal r center of mass omega squared equals L over 2 omega squared equals 0. Right? Because the thing's not rotating. Okay. Okay, I'll clarify that. Why is it not rotating? Because we're talking about immediately following release. Right? So it's not moving yet. So it's just that instant after it starts rotating. So then we have acceleration tangential, right, is equal to r angular acceleration. And now more plugging in ACM in the y direction is equal to ACM in the tangential direction. Oh, I should be clear that this is in the centripetal direction, so I'll put a little sub c on there. Okay, hopefully that makes sense. So r cm alpha, right, translating between linear kinematics and rotational kinematics. And then we know this angular acceleration from the first part of the problem. This is L over 2, 3g, 2L equals 3/4 g. Okay, hopefully my hands aren't in the way. Okay. Now we just sub in some stuff we have from up there. Pretty easy. And we have mg minus fa equals m3/4 g. And then we solve for fa is equal to 1/4 mg. That gives us the second part of our problem. All right. So in order to keep this thing from breaking or wearing down, we have to be aware that that pivot's going to have to take some force equal to 1/4 mass times the acceleration due to gravity. Okay. So that's all I really wanted to get through in this lecture. And I'm going to show you that, or rather email you this when I email around this lecture. But in the old book, there was this really nice table. It's not in the new book. So I'll just talk about it now for a moment, and then you'll see it in your email. Over here, we have all of the linear motion equations, right, that you're used to. And then over here, we have the rotational equivalents. And as I was saying earlier, oftentimes, or nearly always, I guess, you just take the rotational, or excuse me, you just take the linear equations and you plug in the correct rotational quantities, and you get these new equations that deal with rotation. So I'll send this around also. Okay, hopefully this was comprehensible. I promise things will improve as I get better at doing this and get a less bootleg audiovisual setup or whatever, other than my just broken lamp with my crappy camera phone. So yeah, go in the forums if you have any questions, and I will go in there myself and answer your questions. All right, best of luck. Let me know how this is going. I was about to say see you soon, but I probably won't see you for at least half a year. I was about to say I'll talk to you soon, but you will hear the sound of my voice again soon. Have a lovely day.